Vigotsky. I'm a Ph.D. candidate in biomedical engineering and a master's student in statistics at Northwestern University. And today I'd like to give this lecture on the logic of inferring muscle hypertrophy from surface EMG amplitudes. So if you look through the exercise and sports science literature, you'll see claims like this all the time. So they're acute surface EMG studies, and they'll compare exercises and loads, so on and so forth. And in this study, the authors had in the discussion, heavier loads may provide a more potent training stimulus due to both an increase in total muscle activation and torque requirements. So the logic here is because, in part, EMG amplitude was greater, that heavier loads will provide a more potent training stimulus. And this is seen throughout the literature, and it's problematic for several reasons, which I'll get into. But first, I'll address the elephant in the room, which is that I'm very guilty of this. So that quote from before is actually from my first study, which was published in 2015. And since then, we've made allusions to similar ideas and either implicitly or explicitly made similar conclusions in other studies. But it wasn't for a few years that I started to get smarter and started to think critically about these things. So in around 2016 or so, 2017, Stu Phillips, myself, and several others started writing letters to the editors for these types of inferences. So these specifically pertained to EMG amplitudes under fatiguing conditions with high versus low load. And more recently, Israel Halperin, Greg Lehman, Gabriel Trajano, and Tyann Vieira and myself wrote this review, which was published in Frontiers in Physiology, and it's received a lot of attention. And in this review, we kind of go through what is surface EMG, what can it tell us, what can't it tell us, and how should we start to think about these types of inferences. And the community seems to respond well to it, but I think it may have been for the wrong reasons. So a lot of people were citing us. So this is from last year, or rather much, much earlier this year, and there were 60 citations. As of right now, it's about double that. And a lot of these citations are miscitations, so people are citing us for the wrong reasons. Specifically, they'll cite us, for example, to say that there are limitations with drawing these longitudinal inferences. But they don't really appreciate the fact that what we present in the paper undermines the conclusions of their paper, undermines the premise of their paper. It's not that it's just a limitation, it's that it's a fatal flaw, potentially. So I think first we have to try to understand, why are people using surface EMG to imply hypertrophy? And I think there are a few different reasons. So first and foremost, surface EMG is super convenient. So if you want to do a surface EMG study, you have most people come to the lab maybe once or twice, and you slap electrodes on them, have them perform some exercises, and then you just compare the amplitudes. It's pretty straightforward to do. This is in contrast to training studies, which require people to come in usually multiple times for weeks on end, and you have to get them to keep coming back and pushing them through this protocol. So these longitudinal studies are extremely difficult, and it's hard to get high retention rates and enough subjects. In addition, being in academia, publishing is incentivized, so a lot of places will look upon more publications as being very favorable, whereas if you just have a few high-quality publications, it may not be immediately clear that those publications are really high quality. The university may not appreciate that. Grant reviewers may not appreciate that, so on and so forth. So there's an incentive structure that kind of may help give rise to the number of surface EMG publications that we see. In addition, people, I think, really believe surface EMG is informative for hypertrophy. So it's not just an issue of convenience or people trying to game the system. People do think they're doing good work, and I think these are good people. They're not trying to do anything malicious. But I do think there is some logic which kind of undermines some of the logic that's going on here. And I'll kind of go through some of that. So I'll be focusing on that last point. And so I think we need to kind of appreciate this logic first. So why would surface EMG predict hypertrophy? And there are multiple steps here. So premise one, or the first step, would be that surface EMG is a proxy for muscle excitation, where muscle excitation is the electrical signal that travels across a muscle fiber. Then muscle excitation would lead to muscle activation. So while excitation is the action potential that travels across a muscle fiber, activation is when calcium binds to troponin so that the actin and myosin filaments can bind and create a cross bridge. The third is that muscle activation leads to muscle force via cross bridging. Muscle force triggers muscle protein synthesis, and then muscle protein synthesis is what builds muscle. Therefore, the implication is surface EMG amplitudes imply greater hypertrophy. So we're going to address each of these herein. So the first one, does increased surface EMG amplitude imply greater muscle excitation? And this is a study that came out a few years ago by Tyan Vieira and his colleagues, and it's really quite elegant. So what they did was they put a grid of electrodes on the tibialis anterior, and they stimulated the fibular nerve. So what this meant was the person didn't contract at all, the person just remained passive, and the experimenters stimulated the nerve so that they could control all of the neural input to the muscle. And then they measured the response on the grid electrode via surface EMG. And what they found was when you change the foot position, so changing the ankle position, you get different EMG amplitudes. So as you can see here, this is for a bipolar surface EMG amplitude. It decreases by almost 50% as you go from the dorsiflex position to the plantar flex position, which is pretty substantial, especially when in these different exercise studies you might be talking about a 10%, 20% difference. This is applying the same neural input, but you're getting a 50% decrease just by changing the joint position. And this isn't the first time that something like this was noted. So this is from a study in 1982. And I'll just read this quickly. However, it was recognized that any change in EMG when a new joint angle was chosen might have simply reflected an alteration in the geometric relationship between the motor unit generators within the muscle belly and the surface recording electrodes. An allowance was made for this effect by measuring changes in the rectified and average tibialis anterior M wave following maximal stimulation of the peroneal nerve. It was found that the M wave response measured in this way usually changed by an amount proportional to the alteration in EMG activity. So this meant when they stimulated the nerve, this accounted for the difference that they saw between different joint positions. So that the difference in joint positions wasn't really due to differences in voluntary excitation of that muscle. It was actually due to the geometric properties of the tibialis anterior, so how those action potentials were traveling in space relative to the electrode. And here's another study that's more recent and perhaps more relevant to resistance training. And what they did was they looked at two different bench press positions, and they looked at different points on the pectoralis major. And what they could do by putting grid electrodes on these is they could look to see how innervation zones shift between different joint positions. So when you're at 20 degrees of glenohumeral abduction versus 110 degrees, there's a shift in the innervation zone, which means that if you have your bipolar electrodes in one place, so let's say right here, then you're going to get a really low signal when you're at 110 degrees just because the innervation zone changes. And that's by the nature of the muscle contracting and changing position relative to the skin. And this is another study by Jim Potvin. So this is in 1997, and it's a pretty classic study for demonstrating this. So it's really nice. So they had people doing concentric and eccentric elbow flexion, I believe it was, and they looked at EMG amplitudes. And you can see that even holding joint position constant, there seems to be an effect just for eccentric versus concentric. Otherwise, we'd see similar spikes in eccentric and concentric. So it's not just joint position, but it's joint velocity or muscle velocity that also matters. And in addition, there's some theoretical concerns. So if a muscle recruits fibers from deep to superficial or superficial to deep, for different surface EMG amplitudes, so you might have similar motor unit recruitment for different EMG amplitudes. And that's kind of depicted here. So in case 1, you have a much higher EMG amplitude when you have only a single muscle fiber recruited, whereas for case 2, when you recruit from deep, you have a much lower surface EMG amplitude. So surface EMG amplitude doesn't necessarily reflect muscle excitation. So there are some things here that kind of decouple those relationships. Rather, surface EMG amplitude is influenced by a lot of things, so muscle architecture, fiber length, velocity, recruitment strategy, in addition to the biochemical environment, especially when you have fatigue coming into play. Next would be, does increased muscle excitation indicate greater activation? And this is adapted from a classic paper, but the idea is we have neural excitation coming in, then we have activation dynamics, so excitation contraction coupling, and then we have actual muscle activation itself. So we're going to look at this more closely, and this relates to when you actually get the action potential from the nerve and it releases acetylcholine, that triggers an action potential on the sarcolemma, which then causes calcium to be released to bind to troponin. However, this calcium takes time to move through the cell. So it's not an instantaneous thing or nearly instantaneous like the flow of electricity on the surface of the muscle fiber membrane. And this can be represented as a differential equation, but the key point here is that there's a history dependence. So it depends on the rate of change of activation. And it also depends on excitation. So this term really complicates things. So it's a dynamic process that's slow. And that will further decouple this relationship between activation and muscle excitation. And it kind of complicates this. So in some instances, increased muscle excitation will be indicative of greater activation. So if the system is stationary with constant force, non-fatiguing, and isometric, this will hold. But if this system is not stationary, so like dynamic contractions, fatigue, varying force, things like that, then no, this relationship, we really can't depend on it, since there might be some uncoupling. And next would be moving forward in this, does increased activation indicate increased force? And we have to look at the muscle contraction dynamics here. And that's demonstrated by this classic length tension and force velocity relationships. And you can see this is really not too, these are very nonlinear relationships. So if we look at just the length tension relationship, it's possible that we have, say, a fiber length of optimal in one position with, let's say, what is this, 60% activation, but we have, sorry about that, 100% activation, and it's a fiber length of, let's say, 1.3 or so. And then it's not the case that increased activation equals increased force. In that case, increased activation would be the same force. So there are things that you'd have to hold constant in order for this increased activation equals increased force to hold true. So in non-fatiguing and isometric contractions, this would hold. But if the muscle is changing length or if it's fatiguing, this won't necessarily hold, and it's not something that we can really depend on. The next step in the cycle would be, does increased force imply increased muscle protein synthesis? And this is a nice study in which they did, so this is Stu Phillips' group. They had a rest, or so a negative control condition, and they looked at muscle protein synthesis, and this was so 90% of 1 rep max to failure, work matched 30% and 30% to failure. And as you can see, increased force, which would be the 90% to failure, doesn't create greater muscle protein synthesis responses when you go to failure. So 30% versus 90%, the 30% is actually higher in some instances. So this does not hold here. But the relationship is moderated by whether sets are taken to failure. So if the sets are not taken to failure and they're work matched, sure, maybe this holds. But if fatigue is not controlled for, then this seems to be the case. So there's some nuance to all of this. So the next one is, does increased muscle protein synthesis increase hypertrophy? And this is from the classic Mitchell paper, again from Stu Phillips' group from 2014, where they showed pretty much no correlation between muscle protein synthesis taken before training and muscle volume measured over the course of a training protocol. But this is kind of challenged more recently by Damas et al., in which they looked at, okay, what happens if we look at this relationship very early in the training cycle, or if they look at it in the third week of training, or if they look at it in the last week of training. So this is perhaps the more interesting point, and you do start to see pretty strong correlations after you account for this initial training week, which might be associated with muscle damage. So the idea being that there's too much muscle damage in the beginning of training for this relationship to really hold. But this kind of complicates things, right? So we have to ask the question, what if these premises did hold? Well, there's the first issue, which is that correlations are not transitive. So if A is correlated with B and B is correlated with C, that does not imply that A is correlated with C. And this can be kind of represented graphically, and I really like this. It's from a book, How Not to Be Wrong. And we can think of A and B and C, and 1 and 3 are completely orthogonal to one another. So this is an instance where 1 and 2 could have a correlation of 0.7, 2 and 3 could have a correlation of 0.7, and 1 and 3 could have a correlation of 0. So what this really says is we actually need to validate surface EMG as a predictor. But there is some work that kind of spans multiple premises too, which should be noted. So first, surface EMG is not strongly correlated with muscle activation. So that's from Morton's, from Stu Phillips' group. Muscle activation is not strongly correlated with anabolic signaling, again from the same study. Surface EMG is not strongly correlated with anabolic signaling, but it seems to yield different signals in conditions that yield higher versus lower muscle protein synthesis. So this work really, I think, needs to be fleshed out a bit more. Muscle activation is not necessary for growth, so this is from the old stretching studies. These are animal models, I'll note. And there can be identical excitation that can produce different hypertrophic outcomes. So in this study, they had, I think it was a rodent model, and they had different joint velocities, and they gave the muscle the same stimulation. And there's indirect evidence in humans as well. So there's some evidence in favor of surface EMG implying hypertrophy, specifically in single versus multi-joint studies. So for rectus femoris, for example, you don't typically see very high surface EMG amplitudes for rectus femoris in multi-joint movements, but you do in single joint movements. And the same is true for actual hypertrophy of the rectus femoris. So you tend not to see a lot of hypertrophy in multi-joint movements, but you do for single joint movements, namely the leg extension. There's also quite a bit of evidence not in favor of surface EMG implying hypertrophy, though. So, for example, across contraction modes, eccentric versus concentric, fatiguing conditions, so high load versus low load. High loads typically have greater surface EMG amplitudes, but you see similar hypertrophy. And also across muscle lengths. So there's some studies that quadriceps EMG. It's not very reliable across the entire range of motion, but you tend to see greater growth at longer muscle lengths for the quadriceps. And I should also note, there's been some work using T2 MRI, so this looks at fluid shifts. So there's Wakahara's pretty well-known studies which look at regional differences in muscle activation as assessed with T2 MRI, and they look at how that relates to hypertrophy following the end of a training period. And this newer study also did something similar. But there are a couple of things to note here. First is that their statistical models weren't really appropriate. So Wakahara didn't actually calculate a correlation, and this study, they calculated correlations, but I think they could have done it in a better way. But even if statistical models employed directly assessed if T2 MRI implied hypertrophy, it does not follow that the same would be true for surface EMG. So these are kind of assessing a different construct. Now, some will argue that T2 correlates with surface EMG, but that's only been validated in very extreme conditions. So looking across loads within individuals, and this is not exactly what they were assessing here. So to wrap up, the assumption that surface EMG findings are predictive of hypertrophic outcomes is based on weak premises. And in a sense, it's a slippery slope. And a slippery slope is only as strong as the link between each of the links in the causal chain. So if one of them is weak, then the entire thing almost falls apart. You can't really depend on that chain anymore. With or without weak premises, the direct claim has not been rigorously tested. So in research, ideally, we kind of test things directly. There's indirect evidence that it may be informative for hypertrophic outcomes in some contexts, but again, not in others. So there's evidence for it and against it, so it's kind of equivocal in terms of indirect evidence. And this does not imply that surface EMG cannot inform us about hypertrophy. It's really that the premises are weak and we don't have good evidence. So we're not saying that this absolutely is not the case. It's just that it hasn't been shown to be the case. So we're kind of agnostic about it. But in the end, we think it's important to be critical. So when you read a paper or think about these things, always think about what is the author's logic, what assumptions are baked into that logic, and are those assumptions reasonable and are they supported? And in this case, I've kind of laid out that logic and those assumptions, and I don't think a lot of these assumptions are reasonable and supported. So in that case, I think we need to carry out the literature or carry out the work to really test them. And I think these things need to be assessed and met with criticism. I'd like to thank my co-authors of that review. So Israel, Greg, Gabriel, and Tyon. They're all super smart, great guys that have really helped me think more critically about these things. And thank you for listening. If you have any questions, please feel free to email or tweet me. Thanks.